All right, good morning, everyone. I hope you enjoying your weekend. So we'll get started. First, I want to remind you guys tomorrow you will have your homework number 8 due. Okay, so it's tomorrow night it's due. Make sure you work on the problems before that due time. And then number 9 will be due a week after that, and then we'll have our exam 3 after the break. So I originally thought about putting it before the break, but um, since last time on exam 2, you guys didn't do very well, or I should say probably you guys didn't do well as you expected. Um, but that's the nature of the class. So second exam on physics 2, usually the average is around 60 something. So this time you guys had an average of 60, and then these are the breakdowns of what you have. Um, on exam 1, you guys had a 72%, and then this one you had a 60%. But exam 3 will be a little bit easier than exam 2, and then final exam will be easier. Okay, so the next 2 exam will be easier, but still, you guys should um, prepare ahead. So I just want to remind you guys that so physics is not a class that if you just study the day or a couple of days before the exam, then you will be doing good in the exam. That doesn't work. Okay, so make sure you start preparing the exam as soon as possible. So now we have about 2 weeks, more than 2 weeks, and then there's a break. So use those days well, prepare for the exam. Okay, so also you guys can ask help from Kayla or me. I guess you can send me an email if you prefer, or set up a Zoom meeting if you have questions about that. Okay, so I think that's the reminder items. We will get started with the lecture. So we'll be again looking at chapter 23. Let's start with what we learned last time. So last time we took a look on an RL circuits. Okay, so an RL circuit is you have an inductor, so it's a number of coils stacking together. That's an inductor in the circuit with a resistor. And this is in many ways is similar and analog to the RC circuit. Okay, so both inductor and capacitor, they will store energy if you supply the um, circuit with power. Then energy will be stored either in the inductor or capacitor. Okay, so for inductor and RL circuit, if you supply the circuit with the battery, then actually the current in the circuit will go up slowly as a function, exponential function listed over here, where I naught is equal to epsilon divided by R. Epsilon is the voltage the battery can supply. Okay, and 1 minus exponential minus t over tau. So similar. So this exponential function is similar to you when the exponential function in the RC circuit where tau and this time is equal to L over R. In an RC circuit, your tau is equal to R times C. Okay. All right. Now, if you have energy stored in the inductor, then you can flip the switch to number 2. So then the energy stored here can be withdrawn and to power this guy, the resistor. Okay. Or actually the other way around. This is the inductor. This is the resistor. All right. So in that case, if you flip your switch to 2, then the energy stored in the inductor will be consumed by this resistor. So the circuit will have a current that decrease down exponentially given by this equation I equal to I naught exponential minus t over tau, where again I naught is epsilon over R and tau is equal to L over R. Okay. So today we are going to look more into details about the different elements in actually in the AC circuit. So we have been looking at DC circuit, which means direct current circuit. So in that your voltage or current doesn't flip directions. Now, as you know that, or you might probably know, I think most of you guys know that the power we used in our household or here, it's AC circuit, which means the alternating current. So that means at some point, at some time period, your voltage positive, then another time it will be negative, and it's alternating. So it's given as a sine function, right? So you have half of the time your current or voltage is positive, and then half of the time your current or the voltage is negative. Okay, so the voltage is given as a peak value VR, peak times sine of omega t. Omega is the angular frequency. Okay, so for example, what we have here is frequency of the electricity is 60 hertz, then angular frequency is 2 pi times that frequency, okay, in this function. And let's take a look on the simplest element. You have a resistor. If this is powered by a AC current or AC source, power source. According to Ohm's law, voltage across the resistor should be equal to the current going through it times R. Okay. Now we have R, so we have VR, so that's the power, AC power. So then current is equal to VR divided by R equals to VR peak value divided by R sine of function. Okay, so if you do VR peak divided by R, we call it I peak. So then your current will also have a peak value. Okay, times this sine function. Okay, so you can see the current. This is the current. A peak value times sine of omega t. This is the voltage across the resistor. It's a peak voltage times sine of omega t. Okay, so they are having the same sine of omega t. Okay, so this means when you have voltage supplied to the resistor as a sine function, then the current as the result of the voltage applied across the resistor is also a sine function. Okay, so in this case, both the voltage and current, they are the same sine function, exactly the same sine function. There's no phase shift in the sine functions of the two, the voltage and the current. So we call these two in phase. Okay, so the current and voltage are in phase because they will peak at the same time. They will have minimum at the same time. Okay, also peak at the same time in the negative side, and then we will have minimum of 0 at the same time, and then they will have a peak at the same time as well. Okay, so when the voltage and current are having peaks at the same time, we call them in phase. Okay, or in another way, they are having the same sine function. All right. Now, because the voltage and current, they are both in a sine function, they are both a sine function. So if you do the average of voltage and current, they will be 0, right? Because average of sine function is 0. All right. So then if you want to describe, like for example, how much power is being consumed by the resistor, in this case, then the average of the voltage or average of the current doesn't really do a good job because then it will just tell you 0, right? But that's not the case. So instead, we will use root mean square quantities here. So root mean square of voltage and root mean square of current. Okay, and then this is just a quick review for root mean square quantities that we learn in thermodynamics when we describe the motion of the gas molecule. So the root mean square quantity of x, of quantity x, all right, that is equal, so this is the root mean square of x. Okay, that's equal to, you take a square root of the square of that quantity and average of it. So then it will be square root of this guy will be equal to square root of this. So 1 over the square root of 2 x max. Okay, so then the root mean square of a quantity is equal to the maximum of that quantity divided by square root of 2, basically. Okay, all right. So you can see if you are doing root mean square, you square the quantity to get this, and then if you average out that, they will give you half of that. Okay, of that square. All right, so once we have that, we are using the root mean square quantity, then we can calculate the power consumed by a resistor if you supply the resistor with the AC power. So then power is equal to I squared times R. Okay, that's according to definition for power, or one of the equations you can use to calculate the power by a resistor. It's I squared times R, and then if you use I squared, which is the sine function that Kabal slides back, current equal to I peak, right? Then if you square it, current is I peak times sine of omega t, and then you also square the sine term, and then times R. So this is just rearrange of the terms over here. You put the constant terms before the sine function. Okay, so I square peak R sine square omega t. All right. Then to calculate the average power, you average this term. Okay, so you average this expression. So I square peak and R, they are constant terms, so the average will be still themselves. Then the sine is a varying, will have a varying value. So if you average the sine of omega t square, okay, so if you do sine, average will be 0, but if you do sine square omega t, then it's not going to be 0, okay? So that will give you, this will be giving you the root mean square, okay? Quantity of I. So if you do that, if you do I sine omega t square them and then doing average, okay? So then the result will be the root mean square of current, but you squared it. So it's root mean square of current square times R as the result, okay? All right. So then power consumed will be equal to I square RMS times R, right? You'll be using RMS quantity. Again, a specification for your electronics, they are in RMS. So for example, the current, the voltage, right? So they are in the root mean square quantities. All right. Now, similarly, if you would calculate this power in another way, and as I mentioned, there are 3 ways I'm doing it. So if you do V square over R, then you'll be doing V peak sine omega t square. So that means V peak square sine omega square, and then divided by R. Okay. So if you do the average of it, again, V square peak sine square average will be giving you 1/2 of V peak square divided by R, which this 1/2 V square peak is equal to the root mean square squared, okay, divided by R. So then power average is equal to V root mean square square divided by R. Okay, so similar to V square over R, but you'll be just using root mean square quantity. Okay, root mean square of voltage. Also, a third way of calculating the power consumed by a resistor, you can see it's going to be similarly, you can prove this, it's going to be using the root mean square quantities of voltage and current. So the average power is equal to root mean square voltage times root mean square current. Okay, so those are 3 expressions, similar to what you would have for a DC circuit, but you will just be using the root mean squares, okay, quantities. All right, so that's for a resistor in an AC circuit, okay, or a resistor powered by an AC source. Now let's take a look on inductors. All right, and then we'll be looking for looking at the capacitor later. Okay, so for an inductor, so if you supply an AC circuit, AC power to it, okay, so then as we mentioned earlier, when we take a look on a inductor in a circuit, so it will oppose to the change of the current or the that caused the change here, because then there will be current going in through this guy, right? So this inductor will have the opposing effect to that. So due to that, if you supply voltage across that, so current response is actually having a lagging effect. So because it's kind of opposed to the change of it, okay? So in that sense, if your voltage has a peak at t equal to 0, then the current will have a peak because it's not immediately you will have a peak in current, okay? but because this inductor is opposing to the current increasing. So current increase slowly, so starting from 0 and then up, okay? So your current will peak at a time later to the peak of the voltage. So your voltage always peak first, and then current follows that, okay, by the amount of 90° in phase, or pi over 4, okay, a quarter of pi, which is 2 pi. Actually, I'm sorry, it's pi over 2, which is 2 pi over 4, okay? So, and then similarly, voltage will 0 first, and then 90° later in the x-axis here, or pi over 2 later, the current will 0. Okay, so in this case, your current is lagged by 90° or pi over 2 to the voltage. Okay. So then there's this response to the voltage applied, and then the current. But still, we can relate the current with voltage, because once you apply voltage, then current will start to build up. Okay, so the current is equal to V divided by XL. Okay, so in this case, we call this XL to be the inductive resistance of your inductor. Okay, so it gets the name of inductive due to its inductor in the circuit. All right. And XL is equal to 2 pi times F times L, or omega times L. L is the inductance of the inductor, and omega is the angular frequency. If you use frequency F, then you multiply by 2 pi, okay, 2 pi F times L. So in that sense, you can see if you have V on the inductor, so that's the equation at the bottom of the slide here, the first equation, is if it's a sine function, it has a peak value, and then it varies with time as a sine function. Then the current will be equal to VL peak divided by XL sine of this time, not exactly the same sine omega t, but sine omega t minus pi over 2. So this indicate your current lags by pi over 2, okay, in response to the voltage, okay. All right. Let's take a look one example on the inductance or the inductive reactance here. So it says an inductor has a reactance of 100 ohms at 80 hertz. Let me just go back quickly here. So for the inductance, so it has similar effect as a resistance. So then it has the same SI unit for resistance. So this one would also have SI units of ohms. Okay, so it's not on the slides, but you want to take a note on that. Inductance, inductive reactance has SI units of ohms. And as you can see, inductive reactance is equal to 2 pi F times L. So then it also depends on F, the frequency, right? So if you have an AC power that has different frequency, then the same inductor in different in response to different frequency will have different reactance. Okay, so it's also proportional to the frequency here in this case. Now let's take a look on this one, this example here. So it says a reactance of 100 ohms at 80 hertz. What's its inductance? So L, you're looking for L. And then what's its reactance at another frequency, 160 hertz? Okay. So you guys can give it a try, and then we can take a look on the solution together in 1 or 2 minutes, okay? All right, so let's take a look on this one here. It tells us that the reactance of this inductor is equal to 80 or 100 ohms. Okay, so XL is equal to 100 ohms, and then it tells us the frequency is 80 hertz. Okay, so then on A, you are looking for L. What will be the inductance of this inductor? Now XL is equal to 2 pi F times L. So you are given this guy, you can solve for your L, right? So your L will be equal to XL divided by 2 pi times F. So XL is 100 ohms. So X stands for the reactance, and then the L, subscript L, that is for the inductors, okay? So 2 pi times 80 hertz, right? So that gives you 0.199. For inductance, it's in the SI unit of Henry, okay? So 1.99 each, right? Now B is asking you if you have a different frequency, then what's the reactance, okay? So XL is equal to 2 pi F times L, okay? So you can see this time if your frequency doubles, because 160 is twice of 80, right? So it doubles, then your this guy will also double as well. So it will be 200 ohm, but we can still calculate it. So 2 pi times 160 hertz, and then times 0.199, that's in Henry, okay? So that will give you 200 ohms reactance, okay? So as you can see, you have different frequency, your reactance will be different, okay? So in inductive reactance is proportional to frequency, okay? Any questions you guys might have? All right, if not, we'll move on here. Let me share my screen again. Let me see if this is the right screen. Yes. All right. So when you have an inductor in an AC circuit, now let's take a look on what power does that inductor consume, okay? So power, you can calculate 3 ways, either using V times I, or I squared times R, or V squared over R, okay? Now in this case, we are going to just using V times I, okay? So that's the original definition or original equation for electric power. So the V is a sine function with a peak value, VL as a peak value sine function. And then the current is I peak, right, times cosine of omega t. So let's go a couple slides back here. So this is current I, also has a peak value of V peak over XL, reactance, okay? Then the sine of omega t minus pi over 2 actually is a cosine omega t. Okay, so that's the trigonometry trigonometry identities you can look up. So it's actually a cosine function. All right. So then this is a peak of cosine function. All right. So you can put the constant quantities before the sine and cosine, so you can switch terms around. So V peak, L I peak, sine of omega t and cosine omega t. Okay. Now, if you do sine of theta, sine of angle, this in this case is omega t, times a cosine of the same angle, it gives you sine of twice of the angle. Okay, with 1/2 in front of it. So we put 1/2 the very beginning over here. So 1/2 sine of 2 omega t. Okay. Now you can see this is your power has 1/2 a peak value in V and a peak value in I and sine of 2 omega t. If you average this power, okay, so the constant terms, the 1/2, the V peak, I peak, they still remain. And then if you do the averages, it's still the same, right? Because they are constant numbers. But if you do average of sine, function, sine of 2 omega t. So it's a sine function. It's going to be oscillating around 0, right? So then if you average that, it's going to be giving you 0. So this term average of it will be 0. So the power consumed by an inductor in an AC circuit this time, it's going to be 0, right? So that means it doesn't actually consume power if it's an ideal inductor, okay? If we can ignore its resistance. So then, therefore, an ideal inductor in an AC circuit does not consume any power, okay? It only stores energy, right? It stores the power going through it over time. And you can actually take that power out or take the energy out later, right? So that's what we saw when we have RL circuit. If you have RL circuit, you put power source to it, and then after a while, you can remove the power source. You can actually take energy out from the inductor, okay? So that's because the inductor does not consume any power, all right? All right. So now, any questions you guys might have an inductor in an AC circuit? Okay, so if you are clear, we'll move on. We'll take a look on capacitors in an AC circuit. Okay, so when you have capacitors in an AC circuit, now again, as you put the source onto the capacitor, actually the charge builds up slowly. Okay, so and then when you reverse the voltage, and then the charge will be released out. Okay, so there's again a response there, but they do not happen at the same time. Okay, so the voltage on the capacitor and the current on the capacitor, um, they actually are not in phase. That means that they do not peak at the same time. So in this case, it's the other way around, that your current will peak first. Okay, so when you're looking at charging a capacitor, you'll see that current actually dies out, right? Current decrease exponentially. So current start with a maximum and then decreases down. And as you build up the charge on the capacitor, though, so then the voltage go up slowly. Okay, so this time your current peaks first. Your voltage actually lags. It's lagging behind the current peak. Okay, so in that sense, your voltage, if your voltage again you express it as a sine function, then you will have peak value and sine function. Then your current actually peaks earlier first. So it can be shown that current is equal to omega c VC V peak cosine theta because it's in advance of the voltage. So it's a sine of omega t plus pi over 2, okay, in this expression over here. All right, so your current goes peaks first, your voltage follows by 90 degrees or pi over 2 again, okay? Similarly, we can say there's a reaction of the capacitor to the AC power source. So I is equal to V over XC, similar to Ohm's law. Okay, so in this case, because it's not really a resistance, so we call it again the capacitive reactance. The name capacitive comes from the capacitor is in the circuit here. So I equal to V over XC. You can see then this time XC is equal to 1 over 2 pi F times C, which is the capacitance of the capacitor. F is again the frequency of the power source. Now you can see your reactance for a capacitor actually is inversely proportional to the frequency. Okay, it's in the denominator here. Or you can say XC equal to 1 over omega times C. Omega is 2 pi times F. Okay. All right. Now, similarly, for a inductor, we can take a look on the power on the capacitor here. So you can do again V times I. V sub C means V on the capacitor. So if this is sine function, then again, peak the current will be a cosine function. All right, so we'll be doing peak in V times peak in I times sine omega t cosine omega t. Again, these two combined will give you a sine of 2 omega t with a 1/2 in front of it. Okay, then if you average the power on the capacitor here again, you'll see 1/2 V peak, I peak, they still they stay the same because they are constants. Sine of 2 omega t sine varies. Sometimes positive or half of time is positive, half of time is negative. Okay, so you average a sine function will give you 0. So again, a capacitor here in this case is similar to an inductor in an AC circuit. Will consume 0 power. Okay, so it only stores energy when it's supplied by a source. Okay, so it stores energy over there, but it doesn't consume the energy. Okay, let's take a look on an example on a capacitor here. It says a 22.0 microfarad capacitor is connected to an AC generator with an RMS voltage of 118 volts and a frequency of 60 hertz. So that's pretty much the same power we are getting in our households. It says, what's the RMS current in the circuit? And if you wish to increase the RMS current, what should you add? A second, or what should you add a second capacitor in series or in parallel? Find the value of the capacitance that should be added to increase the RMS current to 1.50 amps. All right, so let me help you guys start with listing the nodes and then a few other things, informations over here. Okay, so it tells us that the C is equal to 22.0, so micro times 10 to the minus 6 farad. Okay, it tells you that V RMS is equal to 118 volts. It tells you that frequency is equal to 60 hertz. All right, now it's asking you, what's the RMS current? Okay, to find RMS current, you'll be doing current. So similar, it's a version that's similar to Ohm's law when you are using the reactance. So this is a capacitance, so reactive reactance. So X sub C, you'll do current equals to the voltage divided by the reactance. So if you use RMS, it will give you RMS of current. If you use peak, it will give you peak of current. Okay, and then you know XC is equal to, in this case, is 1 over 2 pi F times C. All right. I think I will just have you guys solve for A, and then we can take a look on B and C together in a couple minutes. So give it a try for A, and then we'll take a look on B and C together. All right, so let's get started here. You're looking for current, RMS current. You'll be doing this guy over that guy. We'll be calculating this one first. Okay. So you can calculate that and then plug in there. So as you are familiar with me now, so usually I would just substitute this expression over here and then get final equation first. Okay, so I will do VRMS divided by actually 1 over the 2 pi f times c. So then this term here is the denominator under the denominator, so it can flip up. So it'll be 2 pi fc times VRMS. Okay, so then I can plug in the numbers over there. So IRMS then will be equal to 2 pi times frequency. In this case, the 60 hertz, and then times the C 22 times 10 to the minus 6 farad times my 118 volts. Okay, that's my RMS of voltage. So this gives me 0.979 amps. Okay, so that's my IRMS. All right. Questions you guys might have, or you can just unmute yourself and then speak up. Okay. If not, we'll take a look at B here. It's asking you if you wish to increase the RMS current, so you want to increase your IRMS. Now IRMS is equal to, from here, we know it's equal to 2 pi FC times VRMS, right? So if you want to increase this guy, what should you do if you add the second capacitor to the first one? So then if you add the second capacitor to the first one, you can actually do a replacement of equivalent capacitor to that, right? So you can do either put them in series, one up to another, all right? So that's called the C1 to be the original one, C2 to the second one, or you can put them in parallel to each other. So it's asking you which one would you do in this case if you want to increase your C. So that's the total C. All right. So we can examine these two scenarios. So we know if you put two capacitors in series, then what you get for equivalent CEQ is going to be 1 over C1 plus 1 over C2, right? And then do an inverse of it. Now, on this case, on the second case here, your CEQ will be equal to simply C1 plus C2 if they are in parallel to each other, right? So you are adding a second one here. So then this guy will increase, right? So if you add the second one here, you can see it's going to be make the CEQ smaller, right? Because this is equivalent to 1 over CEQ is equal to 1 over C1 plus 1 over C2, right? So 1 over C1 plus 1 over C2, this would be greater than 1 over C1, right? So then 1 over CEQ is greater than 1 over C1. So that means CEQ is less than C1. Sorry. So from here, it's basically 1 over CEQ equals to 1 over C1 plus 1 over C2. 1 over C1 plus 1 over C2 is greater than 1 over C1, right? So that means this guy, the whole thing here is greater than the whole thing on the right. So then CEQ is less than C1, right? So then that's the logic over there. So you want to put them in series, in parallel, I'm sorry. So in parallel to increase this C, okay? So you'll be doing CEQ in this case because you have two capacitors, all right? So then your answer should be in parallel. All right. And then in C, it's asking you find that value of the capacitance that will increase the RMS current to 1.5. Okay. So in this case, then we'll be doing starting from here. I RMS is equal to 2 pi f of C. Let me just use CEQ of this guy. Okay. If I can find this guy, then I can find this one because this is given. C1 is given. Okay. Times VRMS. Okay. So my CEQ then will be equal to IRMS divided by 2 pi f VRMS. Okay. And that's equal to, you are given 1.5 as your desired RMS current, 2 pi, 160 hertz, and then 118 volts. So your CEQ is equal to base 33.72 times 10 to the negative 6 farad. Once you have that CEQ, your C2 can be calculated. Okay, so C2 is equal to your CEQ minus your C1. 33.72 times 10 to the minus 6 farad minus 22.0 times 10 to the minus 6 farad. Okay, that gives you 11.72 microfarad, okay, or 10 to the minus 6 farad. All right, that's what you need for the second capacitor. Questions you guys might have? All right. So if not, we'll move on to the next section. We'll take a look on if we have all the resistor, capacitor, and inductor all at the same time in an AC circuit. Okay, so we'll put them simply in series with each other. So then we'll just deal with one current in this case. Okay, so in this case, because you have different elements in the circuit, you have resistance from a resistor, you have inductive reactance from an inductor, you have reactive reactance from a capacitor, or capacitive reactance from a capacitor. So we have all these three different quantities here, R, X, L, X, C, but they kind of are acting similarly to the voltage, right? Because they kind of resist to the voltage, right? Apply. So we call them together as impedance, okay? So that's the combined effect of all those three. So we call them impedance. For individual one, this is called resistance. This is called inductive reactance. This is called capacitive reactance. Okay, but the combination effect of three is called impedance. Or any two of them, you can also call the combined effect to be impedance. All right. So if you have V as, again, peak value, in this case is expressed as V sub 0, V naught, that's the maximum value. It should be equal to V0 divided by Z, where Z is the impedance of the circuit, okay? Or if you're looking for the RMS quantity, RMS current, then is equal to RMS voltage divided by the impedance Z, okay? Now let's take a look on what would be the impedance Z for an RLC circuit or a RC circuit, LC circuit, etc. Okay. All right. So because the peak voltage across those three elements, they do not happen at the same time. Okay. So you can see that the current going through each element will be the same, right? Because they are in series. So in series means they share the same current, okay? But then for the resistor, its current and voltage are in phase. For inductor, its current and voltage, so the current is lagging by 90 degrees. For a capacitor, the voltage is lagging by 90 degrees. Okay, so in this case, you can see for a resistor, the voltage is in phase with the current. But for the inductor, V sub L as the inductor, so this guy actually it's ahead by 90 degrees. Okay, so this case, and then for a conductor, it actually lags by 90 degrees. Okay, compared to the current. So if we add the 3 voltages up, okay, across each the element here, you will get you'll end up with a function like this. All right, so this is the total voltage in the circuit. This is your total current in the circuit. So you can see they are not in phase. Okay. Now the fact that those 3 are not happening at the same time, so this is kind of you want to think about. This is kind of actually so let's take a look on this one. This is in phase with the current, but this one guy is 90 degrees off the current. They're offset by phase. So you can imagine if you have 2 vectors, one is parallel to the other. Okay, so then this is parallel, VL is parallel to, oh no, the perpendicular, sorry, it's 90 degrees, so it's perpendicular. And then VC is also perpendicular to this guy, but in the other direction. So to get the total, you should think about there's one, say if this is horizontal direction, this is vertical direction, and then this is minus of vertical direction. So then the final will be having this relationship. Okay, it's kind of the Pythagorean theorem, or for the magnitude of a vector. Okay, it's the x component plus the y component. In y component, these two are in the y direction. This one is in the x direction. So this is 90 degree with this guy. This is also 90 degree with that guy. Okay, but those two are opposite to each other by 180 degrees. So you can subtract them off each other. So this will be the total voltage. Okay, it's the voltage on the resistor square plus the difference of the voltage on the inductor and the capacitor square. And then we should be looking at its peak values. Okay, so the peak values is equal to this equation. Okay. All right. So then Z in this case, peak value is equal to that. Peak value is also equal to this guy. And V0R is I0 times R. V0L is I0 times XL. V0C is I0 times XC. Okay. So then I0, you have I0 across each of the terms. You can single I0 out to be in front of the square root. So then it becomes I0 square root of R squared plus XL minus XC squared. Okay. So you compare this to this. You'll see I0 and I0 cancel out. So Z is equal to the square root of R squared plus XL minus XC squared. Okay. So then the impedance for RLC circuit then is equal to this equation. Z equals to square root of R squared plus XL minus XC squared. Okay. All right, so that's the equation for impedance. Impedance is equal to resistance squared plus inductive reactance minus capacitive reactance square. Okay, so it doesn't matter which one goes first in the for the XL minus XC. You can do XC minus XL because you squared it. Okay, doesn't really matter. All right. Now, I would like to point out if you just have RL circuit, then your impedance, okay, so then will be just coming from this guy and this guy. So then you are going to just ignore the XC if it's just RL circuit, okay. On the other hand, if it's just RC circuit, then you can just ignore this guy. It will be R squared plus XC squared, okay. So those are two different scenarios there. I don't think we have time for the example here today. We only have about 2 minutes left now. So I will stop here for today. Okay, so we can come back on Wednesday for the for this example. Okay, so I will see you guys on Wednesday then. Bye.